As you may recall, a function has, for each x value, there is a unique y value. Okay, which means that this function has to pass the vertical, any function must pass the vertical line test. So each x value, every input, there has to be a unique output. You can't have two different outputs for the same input. For a one-to-one function, so with a regular function, every x value has to have a unique y value, but there's nothing that says two different x values can't have the same y value. So for example, the line y equals 4, a constant function where every x value is mapped to 4, is a function. It passes the vertical line tests, and for each x value there's a unique y value. It just happens to always be 4. A one-to-one function doesn't work that way. For a one-to-one function is a function, so it has to have the same properties as a function, where for each y value, there is a unique x value. So for a one-to-one function, if you knew that y was equal to 4, you would be able to pinpoint exactly which x value had given you that 4, because each x value will give you one and a unique y value and a y value that no other x value gives you. So the one-to-one function will also pass the horizontal line test. And I find this easy to see with graphs. So let's take a look at two quite common polynomial functions. Let's actually take a look at 3. So we have a line, a linear equation. As you can see, every y value will give you a unique x value, and every x value will give you a unique y value. So we can draw these vertical lines, they only cross one point. We can draw these horizontal lines, they only cross one point, no matter how we draw them. So this is a one-to-one function. A parabola, on the other hand, is not one-to-one, and we can abbreviate one-to-one by writing it just like that. So a parabola is not one-to-one because, for example, when we have x equals 4, we have, if this is y equals x squared, so when x equals 4, y equals 16, and when x equals minus 4, y also equals 16. For a one-to-one function, if we had the y value of 16, we would want only one x value that gives us that y value. And if we have, say, y equals x cubed, this function is one-to-one, as you can see each. So if you had x equals 3 and x equals negative 3, you would get positive or negative 27. So there would be different numbers for both of these. Okay, so we can define formally a one-to-one function so that f of x1, so our y values are not equal. You won't have any equal y values whenever the x's aren't equal. Whenever x1 is not equal to x2. An equivalent way is, or when x1, when we have two x values that are equal, that's the only way that we get given y values. So when we have f of x1 equals f of x2 only when x1 equals x2. So if we have two y values are the same, that implies that the two x values are the same. Okay, so let's have a quick look at an example. Okay, so let's show algebraically that f of x equals x squared plus 2 is not 1-to-1. Okay, so when we're showing that something is not true, we are allowed, if we're trying to show that something is, we need to prove that it's true for all values. So if we're going to show that something is a 1-to-1 function, we need to actually go through and take f of x1 and f of x2 and show that x1 has to equal x2. In this case, because we're asked to show that it's not 1-to-1, we don't have to do that. The burden of proof is not on us. We don't have to prove it for every value. All we need is what we call a counterexample. So it takes a lot to prove something, but it doesn't take very much to prove that something's not true. A counterexample is one example where it doesn't work. And a counterexample is a really useful mathematical and logical tool, which is if you say, for example, in a non-mathematical sense, I always do my homework, and your teacher's like, what about last Thursday? And you're like, oh yeah, I guess I don't always do my homework. It doesn't take that much to prove that something's not true. Okay, saying that something is true all the time is a pretty big statement. So how do we show that this is not 1-to-1? Well, what we can do is if we say f of x1 equals f of x2 only when x1 equals x2, we can try to find one y value that has the same x value. So let's pick a y value that we think will have two different possibilities for x. Okay, so let's try, for example, x equals 6, f of x equals 6. Okay, and yes, I did pick this one a little bit strategically, but you could pick really any number that's part of the range of this function. So let f of x equal 6. So 6 equals x squared plus 2. 4 equals x squared. So x could be plus or minus 2. So this is two x values with the same y value. So this is not 1-to-1 because we found an example where one y value gave us two different x values instead of giving us the same x value. We would be able to show that the two x values have to be the same. Okay, so why do we care when functions are 1-to-1? Well, 1-to-1 functions allow us to define an inverse function that always works. It's possible to have inverse relations, so inverses that are sort of partial inverses. And an inverse function is what gives you back the thing you started with. But with partial inverse relationships, some information is lost. So if I say, well, I took a number and I squared it and the answer was 4, what number did I start with? It's not going to be possible for me to do that, to actually say, well, I can tell you exactly what number you started with, given that you told me you ended up with 4, because it could be 2 or it could be -2. And once it's been squared, we have no way of knowing which one. Okay, if we give some hints like it was a positive number, then we've restricted the domain of our original function. We should be able to give a better answer. Okay, but we truly define inverse functions only on 1-to-1 functions for the whole range of a 1-to-1 function. So let f be a 1-to-1 function. The inverse of f of x, which we call f minus 1 of x. And you may have seen this before in the context of sine to the minus 1, cos minus 1, tan minus 1. That is because those are our inverse functions. We are unsigning or uncosigning or untangenting a number to figure out what the angle was. So that is the reason that we are seeing this familiar notation. So this is the unique function that satisfies the equation f inverse of f of x equals x for all x in the domain of f of x. Okay, so if we have f of x equals x plus 5, so we have a linear equation, f of x is x plus 5. How do we plus 5? We minus 5. So if we want to know what we started with, we would take a number and subtract. If we know, well, we added 5 to the number, we would subtract 5 to get it back. So our f inverse of x for this one would just be x minus 5. You take your output, subtract 5, you get back your input. So what this does is we're linking outputs of one function to inputs of the other and vice versa. So the range of f is the domain of f inverse. And similarly, the domain of f is the range of f inverse. So it maps domain to range, range back to domain. Okay, so if we have a discrete function, we can say, well, f of x is 1 to 2, 3 to 4, and 5 to 6. We can see that this is a one-to-one function because we only have one output for each input, and each output is unique. There are not two inputs that map to 2, 4, or 6. So f inverse would simply take the y's and map them back to the x's. So we would have 2, 1, 4, 3, and 6, 5. Okay, sorry, did I write f prime? That really should be an f inverse, shouldn't it? Okay, we'll get to f prime eventually. Example 3. So we want to show that f of x equals 1 minus x cubed to the 5th plus 2 is 1 to 1, and find its inverse function. Okay, so if we go and we have a quick look back, this time we have to prove that something is one-to-one. So we can't just find a counterexample. We actually have to go back to our definition. So our definition up here says that f of x equals f of x2 implies that x1 equals x2. So what we're going to do is we are going to take f of x1 and f of x2 and show that x1 has to equal x2. And we're going to do all correct mathematics along the way in order to do that. So we will assume f of x1 equals f of x2. And now we're going to plug in what the function is and work backwards to show that x1 has to equal x2. So we have 1 minus x1 cubed to the 5th plus 2 equals 1 minus x2 cubed to the 5th plus 2. Well, we can subtract 2 from both sides. So we get 1 minus x1 cubed to the 5th is 1 minus x2 cubed to the 5th. Now we can take the 5th root of both sides. Because the 5th root is an odd root, there is only one answer. We don't get a plus minus, we only get 1 minus x1 cubed. So 1 minus x1 cubed equals 1 minus x2 cubed. Okay, we can now subtract 1 and multiply by -1, so we get x1 cubed is x2 cubed. We can take the cube root of both sides, and again, cube root doesn't leave us with a plus or a minus. There are no options. There's only one solution for a cube root. So we get x1 equals x2. You can see, though, if either of these was an even root, we would not be able to show that this was 1-to-1. In fact, it, would not be 1-to-1. Okay, so we've proved it's 1-to-1. Now let's find the inverse function. Okay, so therefore, f is 1-to-1. Now, when we want to find the inverse function, what we do, so to find inverse, we switch x and y and solve for y. So we're taking our y's as the input, and that's why that works. So our y's from f of x are going to be the input now, and we're going to see what do we put in to get back the y that is really the x. So we have x equals 1 minus y cubed to the 5th. Remember, f of x equals y, so we're just swapping those around. So we get x minus 2 is 1 minus y cubed to the 5th. We'll take the 5th root, so 5th root of x minus 2 equals 1 minus y cubed. And then we will subtract, I'm going to add y cubed to both sides and then subtract the 5th root of x, and that also gets my y on the right side. So we get y cubed is 1 minus the 5th root of x minus 2. Then we'll take the cube root, so we get y equals the cube root of 1 minus the 5th root of x minus 2. Okay. The other way we can determine inverse functions of 1-to-1 functions is to reflect them over the line y equals x. So our last example, we are going to reflect a lovely function for line y equals x. So we're going to find f inverse given the graph of f of x. Okay, so let's say we have our f, and our f is a lovely function that comes up like that. So that is a lovely 1-to-1 function. So what we're going to do is we're going to draw in the line y equals x, and we are going to do our best to reflect it over. So here we have a y that gets switched with an x, and let's actually do this in a different color just so that we can tell them apart. How about green? So this, our f inverse, is reflected over this line. So we're going to draw as nice of a beautiful mirror image as we can, and it's good to take your x-intercepts and move them to being y-intercepts, and take your y-intercepts and move them to being x-intercepts. And then we have a lovely graph of f inverse. And we don't need to know the equation of the function. We can simply do it geometrically using the line y equals x.